Alright, this video is going to be the more generalized form of the last result that we got about having two endpoints of the diameter and then taking a point on the circle and showing that generates perpendicular line segments. So this is the general form. This kind of, I don't want to say it's a proof because it's not complete like a proof would be, but it's kind of showing the general outline of what a proof would look like. It's like a casual proof of it. That the result we got of those perpendicular lines shows that, I'm sorry, what am I trying to say? It shows that generates a equation of a circle. So in other words, this is an alternate definition for a circle. In other words, the alternate definition of the circle is the equation for the set of all points in the xy plane such that AP is perpendicular to BP. AP would be that line segment and BP would be that line segment. And P here represents, it's our variable that represents all points in that set of points that I'm talking about. And I just wrote it here, but actually P could be here or here or here, anywhere along that circle that A and B are a part of. So here I kind of drew a little diagram really quickly. HK is going to be our center for the circle, and then this vertical line is y is equal to h, and the horizontal line is, I'm sorry, the vertical line is x is equal to h, and the horizontal line is y is equal to k. And then we know that if I wanted a circle with radius r, then I can find these two diameter endpoints on the diameter of the horizontal diameter is going to be h minus r and k, and h plus r k. Those will be the two coordinate points. And then once I know those coordinate points and I have my variable coordinate point, I can find the slopes m1 for the slope of AP and m2 the slope of BP. And these are variable in terms of x and y, and then h, k, and r, those are arbitrary values. I can put any value I want into it. So this is the generalization part that I'm talking about. These are arbitrary values, but I can take any value I want, any radius I want, any position I want for the center of the circle, and then we can follow this form and we can show that generates a circle. So are there any other points I want to make? I guess I could walk through the algebra really quickly. So this part says AP is perpendicular to BP implies that M1, the slope M1, the slope of AP, is equal to the negative of the multiplicative inverse of the slope of M2. And then that, from these two, so I have M1 in terms of these values, and M2 in terms of these values, and then all I have to do is substitute that in to this statement that I know, and then from that we just do algebra to generate the form of a circle. So here I just multiplied the denominator by that numerator, multiplied this denominator by that numerator, and then from here it's a little tricky algebra, but it's pretty straightforward. Here I just kept the h and r and h minus r in parentheses, and I just treated them like numbers until I got to this point, negative x times h plus r minus x times h plus r. And I factored out a negative x, and I'm left with h plus r plus h minus r, and we'll see that r minus r subtracts itself out, so we're left with 2h. And then here, h plus r times h minus r, I can FOIL that together to be h squared minus r squared. And then the other maybe tricky part was I boiled this part down to negative x squared plus 2xh, then moved out to the other side of the equation, and then we completed the square on those terms so that I have a negative h squared here that subtracts out the h squared on this side of the equation that I needed to add to it. Or I guess I could have just put it on the other side of the equation and that would have been just fine. I could have just used it. But I don't know, I was just thinking complete the square mode. So we completed the square on that x squared minus 2hx plus h squared, and then that's when it comes together as the form for a circle. So we could work this backwards, and we could show from this form that any point xy here is going to satisfy this property for the slopes between the two diameter points and P. So it can be worked backwards to show that this is a property that follows from the algebraic definition of a circle, or we can take that property and we can derive the algebraic definition of a circle. So it goes either way. I don't think there's much more I want to say about this topic. I think I'll probably be moving on to the rest of the conic section soon. Maybe I'll come back and do more circle stuff later.